The instant of impact. And to the rescue, a supply bundle is dropped from a helicopter. The bundle's height off the ground t seconds after it's dropped is given by the equation h of t equals 400 minus 16t squared, where with h of t is measured in feet. Suppose the bundle can withstand the impact of hitting the ground only for speeds up to 165 feet per second. That's going to be important. Determine whether the bundle will survive the fall. You need to find out how fast it is traveling when it hits the ground. Keep careful track of your computations in this activity. You can compare results from question to question. So how far does the bundle fall during its last 2 seconds? That is from time t equals 3 to t equals 5. What we found out in the last assignment is that it hits the ground after 5 seconds. And so what I want to actually start off doing is just showing a graph, a sketch really, not really a true graph of when this happens. So we know it's going to hit the ground at 5 seconds. Sneezing. 0. Let's see, 1, 2, 3, 4, 5. Yeah, we can do that. 1, 2, 3, 4 seconds, 5 seconds. Okay. And we know, let's say it starts at 400, and it's going to start off going fast and then, or falling slowly and then move faster and faster, ultimately ending at 0. So our question is, what is the height at 3 seconds? What's the height at 5 seconds? What's the distance, right? What distance does it fall for those last 2 seconds? And what's our average speed over that time? Well, first of all, our height is just this function, right? This line right here is represented by the function h of t. So it's just the function at any specific time. So what we need to find out is, let's see, what question are we on? 1a. We need to find out how far does it fall during the last 2 seconds. So from the time t equals 3 to t equals 5, well, that's just going to be the height at time t equals 3. So h of 3 is going to be 400 minus 16t squared, where t is actually 3. I should have written that as a 3. 16 times 3t squared, which is equal to 400 minus 16 times 9. And we know 16 times 9 is 144, I believe. Let me get out my calculator. Let's see, 16 times 9 is 144. So 400 minus 144 is 256. So you know it's traveled 256 feet is our answer right here. 1b says what's the average rate of change for that? Well, we know if it falls 256 feet and it takes 2 seconds, we can do 256 divided by 2. And that right there is equal to 128 feet per second is our average speed for this case. So let's keep going. Question 2 asks a similar thing, but instead of for the last 2 seconds, it asks for the last second. Well, 1 second before the last second is 4 seconds. And it's the same questions. How far did it fall, and what's the average speed for that last second? So that's just going to be our height now at 4 seconds. So if we can do, just like we did last time, we want to figure out our height at 4 seconds, which is equal to 400 minus 16 times 4 squared. That's going to be 400 minus 4 times 4 is 16 minus 16 times 16. 16 times 16 is 256, so 400 minus 256 is equal to 144 feet. So that's how far this fell, is 144 feet. And 2b is, well, what's the average speed of this? Well, when we just take 144 and divide it by this interval here, well, that's just 1 second, meaning our speed is just going to be 144 divided by 1, which is equal to 144 feet per second. Okay, now we're going to look at question number 3. Question number 3 asks, similar question again, but instead of the last 2 seconds, last second, it's now the last half second before it hits the ground. So we're getting closer to learning the speed on impact. Well, the last half second before it hits the ground is going to be a half second before 5 seconds, and that's going to be at 4.5 seconds. So what we can do is we can say, well, why don't we take, all we're really doing is we're saying we're going to take our height at our final time, which is 5 seconds. We're going to subtract our height at our initial time, which now in this case is going to be 4.5 seconds. And then we're going to divide that by the interval, which is just this right here. So all I did was say our height at this time, our height at this time, which is 0, minus our height at this time, which is, or I guess now for this problem it'll be this time right here, which is this. So it just gives us our change in y, where the bottom gives us our change in x. And now we already know the height at 5 seconds is 0, and so we just need to know our height at 4.5 seconds. So that's 0. Our height at 4.5 seconds is going to be 400 minus 16 times 4.5 squared. And all that is going to be divided by 5 minus 4.5, which is just 0.5, right? It's a half second. That's how long of an interval we're looking at right now. Well, let's figure out what this is. 400 minus 16 times 4.5 squared is equal to 76. So our height that's left is our change in height is minus 76 feet over this interval. And so if we do 76 divided by 0.5, that's the same thing as 76 times 2. So it's 152. And just to be clear, we are falling down, so all of our speeds should be in the negative direction. Great. So that's our speed there. Well, look, we're narrowing it down. We know this package can survive an impact of up to 165 feet per second. Right now, if we look at the speed as it increases, as we decrease our interval, we can see we started off, this was 128 feet per second for this one, 144 feet per second for this one. We're getting a little faster with 152 feet per second for this one. Let's check our next interval. Our next interval asks for us to measure the last tenth of a second. Okay, well, let's do it. Last tenth of a second, that means a tenth of a second is going to be 4.9 to 5.0. So we're going to measure our height at 5 minus our height at 4.9, and that's going to be divided by 5 minus 4.9. We know the height of 5 is 0, minus whatever the height is at 4.9, we'll plug it in. 400 minus 16 times 4.9 squared, divided by 5 minus 4.9. Oops, actually we can just write that as 0.1. So let's figure out what this is. (400 minus 16 times 4.9 squared is 15.84. And since we have that negative, we'll carry it over. So it's negative 15.84 divided by 0.1. Well, if we divide by 0.1, that's the same thing as multiplying by 10, which means that we're just going to move the decimal over one place. So we're going negative 158.4 feet per second. So right now we can still survive the crash, right? And we're getting at a pretty small interval, but we keep kind of increasing a little bit. So the last question asks, what about the very instant it hits the ground? Now what we're doing right now is we keep on, sorry, I'm trying to put my paper. We keep on estimating. We're estimating the instantaneous speed when the package hits the ground. And in this math class, we actually don't have the tools yet to prove and to say exactly what the speed is at the end. That's actually the next lesson is your first calculus lesson. But we're not going to get there in this math class. So we're going to estimate the bundle's speed at the exact moment it hits the ground. So let's take a look. To estimate it at the exact moment it hits the ground, we know when it is actually like on the ground, its speed drops to 0, but we want to know like the tiniest bit beforehand. So we're going to use a smaller interval than 0.1, and our interval is going to be 0.01. And mathematically, theoretically, you can just keep going smaller and smaller, which is actually what calculus ends up doing. You get to infinitesimally small numbers, but we're not doing that. This estimation is great. So we know height of 5 is 0, minus 400 minus 16 times 4.99 squared divided by, this is just 0.01. And let's see what we get. So we can do 400 minus 16 times 4.99 squared. And we've got 1.598. I'm going to round that up to 1.6. Oh, I guess I should do negative 1.6 over 0.01, which is equal to, this is the same thing as multiplying by 100, which is equal to negative 160 feet per second. And that should tell you the instant this hits the ground, it's moving at 160 feet per second, which actually tells us that our package is going to be safe because it can withstand 165 feet per second. Okay, thanks for watching.